Assalamualaikum. My name is Nur Atikah Nadira binti Muhammad Zaidi, and today I will be presenting my final year project on the acid-based treatment of recovered carbon black derived from waste tire. This project was supervised by Dr. Nurul Fataha Ashikin Zainal. In this presentation, we will explore the motivation behind this study, the methodology used, and the results obtained from our experiments. Let's get started. Recovered carbon black, or RCB, is a material obtained from the pyrolysis of waste tires. It has various applications including use in inks, coatings, rubber products, and plastics. The quality of RCB can be enhanced through several treatment processes such as acid-based treatment, dual acid treatment, acid washing, and dry milling. These treatments aim to purify the RCB, improve its surface properties, and remove contaminants. The expected outcomes include increased surface area, enhanced reactivity, reduced impurities, and improved sustainability for various industries, ultimately contributing to economic viability and sustainability. The objective of this study are twofold. First, to investigate the optimal treatment conditions for RCB to enhance its quality, and second, to evaluate the properties of treated and untreated RCB. The problem statement addresses the need to improve the quality of RCB to match that of commercial carbon black, which is VCB, by addressing impurities and inconsistent properties. Achieving this objective will help make RCB a more viable and competitive alternative to VCB in various industrial applications. Tires are non-biodegradable and bulky, posing significant environmental challenges when disposed of in landfills. Recycling methods like pyrolysis decompose tires into valuable byproducts without harmful emissions. RCB derived from waste tire, pyrolysis contains undesired elements and exhibits different surface chemistry compared to virgin carbon black, VCB. The lack of standards and technical approaches for RCB limits its commercial use. This study explores various treatment methods to enhance the quality of RCB, making it more suitable for industrial application and reducing reliance on VCB. Our methodology involves several key steps. First, the RCB is dried at 120 degrees Celsius for 24 hours to remove moisture. Then, it undergoes treatment with various concentration of nitric acid, which is HNO3, and potassium hydroxide, which is KOH. The treated RCB is subsequently washed with distilled water to remove residual chemicals, dried again, and analyzed for ash content, surface area, and functional groups. Techniques such as Brunner-Emmett-Teller (BET) analysis and Fourier transform infrared spectroscopy, which is FTIR, are used to assess the properties of the treated and untreated RCB. Let's delve into the findings from the FTIR analysis. Fourier transform infrared spectroscopy, or FTIR, was employed to understand the chemical composition and molecular structure of the RCB before and after treatment. The FTIR spectra indicated several key features, which is aliphatic hydrocarbons. We observe peaks corresponding to CH stretching vibration, which are characteristic of aliphatic hydrocarbons. These are typically found in carbon-based materials and suggest that the fundamental structure of RCB includes long-chain hydrocarbons. Secondly, aromatic C-double bond C vibrations. Peaks indicating the presence of aromatic C-double bond C were also detected. Aromatic structures are common in carbon black due to the pyrolysis process, which breaks down complex polymers into simpler aromatic compounds. Thirdly, oxygen-containing functional groups. Perhaps the most significant finding was the development of oxygen-containing groups such as CO and C-double bond O bonds on the RCB surface after treatment. These groups were not as prominent in untreated RCB, suggesting the acid-based treatment effectively introduced these functionalities. The introduction of this oxygen-containing group is beneficial for several reasons. They enhance the surface reactivity of RCB, making it more suitable for various industrial applications such as in rubber composites and coatings. They can improve the compatibility of RCB with polymers and other materials, facilitating better dispersion and bonding. Next, we examine the ash content of RCB before and after treatment. Ash content is a critical parameter as it indicates the presence of inorganic impurities which can adversely affect the properties and the performance of RCB. Our results showed a clear trend, which is, firstly, untreated RCB had a relatively high ash content, reflecting the presence of various inorganic contaminants from the pyrolysis process. Secondly, treatment with HNO3. As the concentration of nitric acid increased, the ash content decreased. Specifically, we found that a 6 molar concentration of HNO3 was the most effective in reducing ash content, indicating optimal impurity removal at this concentration. The reduction in ash content has several implications, which is it improved the purity of RCB, making it more comparable to virgin carbon black (VCB). Lower ash content reduces the likelihood of interference with the material's properties, such as electrical conductivity and reinforcement in composites. Finally, let's discuss the findings from the BET surface area analysis. The surface area and porosity of RCB are important characteristics that determine its suitability for application like adsorption, catalysis, and as a reinforcing filler and rubber and plastics. The BET analysis revealed significant improvements in the treated RCB. Firstly, untreated RCB had a relatively low surface area and poor volume, limiting its effectiveness in application requiring high surface interactions. Secondly, treated RCB. The treatment with 6 molar HNO3 notably increased the surface area and pore volume. This suggests that the acid treatment effectively opened up the pore structure and increased the accessible surface area of RCB. The increased surface area has several benefits. Firstly, it enhanced the adsorption capacity of RCB, making it more effective for use in filtration, purification, and environmental remediation. It improved the interaction and bonding with other materials, such as in rubber composites, leading to better mechanical properties and performance. To wrap up, our study demonstrates the significant impact of acid-based treatment on the quality of RCB derived from waste tires. Here are the key takeaways. Firstly, reduction of impurities. The treatment, particularly with 6 molar HNO3, effectively reduces the ash content in RCB. This purification process removes inorganic contaminants, bringing the quality of RCB closer to the VCB. Secondly, enhanced surface properties. FCIR analysis showed the development of oxygen-containing functional groups on the RCB surface after treatment. These functional groups improve the reactivity and compatibility of RCB with other materials, enhancing its performance in various applications. Thirdly, increased surface area and porosity. BET surface area analysis revealed a significant increase in surface area and pore volume in treated RCB. This improvement enhances the material's adsorption capacity and interaction with polymers, making it more suitable for use in industries like rubber manufacturing and environmental remediation. Based on our findings, we recommend further research to optimize the concentration of acids and bases used in the treatment process. Additionally, exploring alternative acids and bases may yield even better results. Advanced analytical techniques should be employed to study the properties of treated RCB in greater detail. It is also essential to evaluate and mitigate the environmental effects of the treatment process. Refining parameters such as temperature, reaction time, and concentration can help achieve more efficient and sustainable treatment methods for RCB. I would like to express my sincere gratitude to my supervisor, Dr. Nurul Fataha Ashikin Zainal, for her invaluable guidance and support throughout this project. Her expertise and insights have been instrumental in the success of this research. I would also like to express my gratitude to the lab assistant and Dr. Fataha's FYP student for their assistance during the experiments. Thank you all for your attention. I am happy to answer any question you may have.